So in thinking about how to partition this, you should think this way. Matrix L inherently has special structure. It's lower triangular. As we march through this matrix, we would like to identify a big block of zeros that inherently you don't need to compute with or that don't come into the picture. If you only partition in one direction, you can't do that cleanly. So inherently, when dealing with a lower triangular matrix, you want to partition into quadrants because that identifies this as a nice big zero, and this block, if square, is then itself lower triangular, as is that. And of course the exact same argument goes for you. Now, matrix A doesn't have any special structure, but matrix A is going to be overwritten with L and U. So the fact that along the way it becomes L and U imposes a structure on it, and therefore you want to partition it into quadrants as well. So the insight is we take our matrix A, we partition it into a top left, bottom left, top right, bottom right. Now that's the matrix with which we're actually going to be working. In order to be able to reason about correctness, we're also going to want to reason about L, which is going to be partitioned into a top left, bottom right, with a nice block of zeros identified there, under the assumption that these blocks are square themselves. And then the same thing is true for U, which becomes U top left, U top right, U bottom right, with a block of zeros right there. Because L is unit lower triangular, L top left is unit lower triangular, as is L bottom right. Now, what do we do next? We take the partition operands, A, L, and U in this case, we plug it into the post condition, and then we manipulate that into a partition matrix expression. Why don't you stop for a second, take a piece of paper, and see if you can work that out.